Hello everyone, welcome to my video. I am Dr. Satyanarayan Rao, and in this video we are going to understand what is Wavelet Transform and why it is used, what are the advantages it has over the Fourier transform that is normally used to analyze time series, and we are going to take a simple ecological example to illustrate what Wavelet Transform can do. We will also see briefly the mathematical expressions for Wavelet Transform and see how it can detect events that Fourier Transform alone cannot do. So as we will go actually more detailed into the Wavelet Transform, I wanted to actually give a specific example that really highlights its utility, the NDVI index. So NDVI index is used in ecological study, and it actually gives us a perfect example for demonstrating why Wavelet Transform is very powerful in analyzing time series data. So I'm going to go a bit deeper on this example, how it is related to ecology, so that it will anchor our discussion on Wavelet Transform. So since this part is a little bit detailed, if you are here just for the Wavelet Transform, you can skip ahead to the next section to the history of Wavelet Transform. Or if you are interested in how Wavelet Transform can be applied in real world scenario, this ecological example can be a bit helpful. To start with, we know that more and more satellites are going to orbit the Earth in the future to actually collect a wealth of information about the urban areas, forests, ecosystems, clouds, oceans, and everything related to our planet Earth. And one such data is related to the vegetation is Normalized Difference Vegetation Index, which is known as the NDVI, and also the soil moisture. So soil moisture and NDVI is the two common index that we collect using the satellite that is more often used in agricultural studies and also to study ecosystems and forests. And so let's consider for now the NDVI index. So this NDVI index is an important parameter that is derived using satellite images, which can tell us about vegetation health by measuring how plants absorb and reflect sunlight. It can also tell us things like how green the vegetation is. For instance, we could have seen different shades of greens in the spinach or different leaves. The NDVI index can quantify how green or how is the chlorophyll content in the vegetation, how healthy it is, because the chlorophyll content is also an indicator of plants' health. It can also tell us whether any of the plants or trees in the forest is going through stress that can be related to insect outbreak or drought or any of the biotic stresses. And so what we get out of NDVI is often a time series data. So we have NDVI index, a time series which is recorded over entire time. And let's consider the NDVI time series. So if we take forest as an example, let's say we collected NDVI time series data on a particular forest. Let's take it as Amazon rainforest, for example, in Brazil. And we know that like rainforests or tropical forests or any forest in general are complex dynamic ecosystems where actually many processes occur at simultaneously at different time scales. So when I look at NDVI time series, I can sense that a lot of things are happening, a lot of changes are happening at different time scales, but I cannot clearly see or draw conclusions just by looking at the raw time series data. If we see what are the things that might be happening in a forest is, we firstly have like yearly cycles or seasonal changes that takes place for example, leaf emerges in the spring or leaf falls in the fall. All these are yearly cycles. So when there is no leaf, you will see that in the NDVI index. Or when there is new leaf that emerges in the spring season, we will see an increase in the NDVI index. And if it's not a tropical forest, plants go into a dormant state in the winter, and so there will be a reflection of this in the NDVI index as well. So these are annual or yearly changes that happens in the forest, and also we see that the maximum peak greenness that occur in the summer season, somewhere in the summer when all the leaves are fully grown and are taking up the sunlight and they are shining in the green spectrum. And if we see like what are the long-term changes, there are some changes like global warming. These are like decades of changes that are very gradual, that we don't see immediately, but they do happen at a gradual phase. There is also plant evolution that is happening quietly in the forest at a larger time scale. And there are also very high frequency events, like sudden events like forest fires or plant disease outbreaks, insect that attacks the forests, or even illegal smuggling of wood. If there is a group that is going and taking out logs of trees, they are cutting down the forest, that you will see it in the NDVI time series, that at certain region you don't see the greenness. And so these are the different changes. So we have three types of changes: seasonal changes, there are long-term changes that happens in the time scale of decades, and also sudden events that can take place in the daily time scale. And so NDVI time series data contains all of this information. So if I look at say 10-year NDVI time series information of a particular forest, let's say, all these changes, whether it is gradual or seasonal or even sudden changes, they are all in the data, but it is hidden, and the challenge is to identify them and knowing that when a particular event occur in time. And when we see time series, what comes to my mind is to apply Fourier transform. If I apply Fourier transform to such a time series, it will definitely give me all the frequency component of the data. It will tell me that there are yearly cycles in the vegetation, there are seasonal patterns, there are also some long-term trends like climate change. Fourier transform will also tell me that there are some high frequency variations that could indicate an insect breakthrough or some smuggling of forest wood, and all these things I will see it as a in the frequency spectrum. But the problem is since Fourier transform cannot localize events in time, I will never know when a particular event happened. So if I see a high frequency variation that would indicate an insect breakthrough or a forest disease or something like that, I will not know when it occurred, because I know it occurred, but I will not know when it occurred. And this is where we need wavelet transform that actually combines both time and frequency analysis. So in the next few sections of this video, we will see what is like the mathematical expressions of wavelet transform and try to understand it in more detail with a very simple example that is related to forest ecology. So let's talk a bit of history of wavelet transform before going into the mathematical expressions. And the wavelet transform actually began with the works of Jean Morlet, who was a geophysicist, and Alex Grossman, who was a mathematician. Together actually they were studying the seismic activity or the seismic signals that come from the earth activity. These vibrations from the earth, these are caused by events like earthquakes or volcanic eruptions or the mantle plate moving. And all these signals, the seismic signals, are important because they tell us about the intensity and the nature of these events. So in this kind of signals, capturing both time and frequency details are essential, and this necessity actually and also the Fourier transform cannot capture that. And this is what led Jean Morlet and Alex Grossman to come up with wavelet transform, where they used small packets of waves to capture both time and frequency story of a signal. And if you are interested more into the history of wavelet transform, I suggest a nice paper by Robbie Poliker from Iowa State University. I think it's open source, and it actually gives a detailed look on how wavelet transform came into existence. And so now let's go into the mathematical perspective of wavelet transform. The continuous wavelet transform, or CWT, can be thought of as a correlation between our x of t, the time domain signal, and the scaled and shifted versions of the wavelet functions, which is small packets of waves that can be scaled in frequency or shifted along the time axis. So mathematically we can write it as the W of, which is a function of a comma b, where we have these parameters which I will explain. A is the scaling parameter and b is the translation along the time axis, is given as the integral of our time domain signal. So here x of t is our time domain signal, and this is our wavelet which can take different shapes, and it can stretch or squeeze along the frequency axis or also scale along the time axis to capture both time and frequency localization. Why we have this? The star indicates the complex conjugate, so that the wavelet actually captures both the phase and the magnitude of our time domain signal. So it captures all amplitude and phase information, and if the phase information is not important for our application, we can choose a real wavelet so that it's a real number. And so this is the mathematical definition of a wavelet transform. And here the psi of t is called as the mother wavelet. Here the A is the scaling factor which actually adjusts the wavelet's width, and the B is the time translator, so it moves along the time axis, shifting the wavelet along the signal's timeline to pinpoint when a specific event occurs, like the previous example that we saw, like when the insect outbreak occurred or when the forest fire happens. All this information is because these wavelets can also move along the time axis. And so once we have the wavelet transform, we can also compute the inverse wavelet transform, where x of t now becomes. So the integral is on the dB, dA, these parameters, and we do have a normalization constant to ensure that the energy is conserved. And so this is how we integrate over these parameters, scaling and position parameters, over our shifted versions of our wavelet and the wavelet transform. So the wavelet coefficients here and the wavelets, the original wavelet that we used to actually transform, we can always use this kind of integral on scale and position parameters to get back our time signal. And so this is the inverse wavelet transform that we are seeing. So as I was browsing through the MATLAB page, the wavelets that we use can come from different shapes. For example, it can be like a square wave. And so this MATLAB page actually gives different types of wavelets that are within the MATLAB. And so for example, here you see we have sines or square kind of wavelet and also like sharp edges. So based on what kind of time domain signal we have, we can choose our wavelet appropriately so that it can capture the maximum out of our time domain signal. So if our time domain signal has sharp edges like sawtooth, it makes no sense to use a wavelet like this with a square wavelet. So for our ecological dataset, let's say we have the NDVI time series, something like this, a decade-long time series, and so we have the drought, the onset of drought somewhere in the year between 3 and 4 in this region. And in the year 7 and 8, we have an insect breakthrough, which is a sudden high frequency event. And so this is what we see here, abrupt changes in the NDVI index due to the disease outbreak. And then the NDVI continues, and this could be like the seasonal patterns, the annual seasonal patterns that I described in the earlier part of this video. And we have like drought and insect outbreak. And let's see how Wavelet Transform can detect this event exactly when they occurred, not just they are present, but we want to know when they occurred. And so for that we will use, as we discussed, we have many different types of wavelets, and we are going to use a specific wavelet that is very commonly used in seismic analysis, also in ecological study. It's known as the Mexican hat wavelet. By definition, we can write the Mexican hat as so. This is the definition of a Mexican hat, and it will look like something like where we have now the t as the time, a is the scaling variable here, and b is the translation parameter, so which shifts the wavelet along the time axis. And so this wavelet actually can stretch or squeeze, like for example it can stretch like this, can stretch, or it can even squeeze like this. So it can, and also it can move along the different time axis because of the translation parameter. And so in summary, this A controls how this Mexican hat is compressed or stretched, and B controls how this wavelet can move along the time domain axis. So what we want to detect with this Mexican hat is that we will have a small a, which is a shorter duration, and B should be around 7 years to detect our insect breakthrough here. And similarly, we will have a medium A around 1 year, and B as around 3 to 4 to detect this drought event. And we also need to adjust our A and B for a larger events like degradation or climate change which takes place. So for this example, we are considering 3 different events. One is the degradation that is happening at a large time scale, the drought, and the insect breakthrough that is specifically happening at the 7th year. It starts at 7th year. You see the pattern breaks and go backs. And so we will apply this Mexican hat. Basically the wavelet transform is correlating this kind of wavelet with our time domain signal, and then we will see what we get. So here is our time signal. In the first panel, what I show here is our NDVI time series showing distinct ecological events, like we have the insect outbreak here and the drought, and also the gradual degradation. If you can see, there is a gradual degradation of our NDVI index. It's gradually decreasing. This is how the Mexican hat wavelets looks like for 3 different scales. So you have the red one, which is at a smaller scale, which is meant to detect events like the insect outbreak because it has sharp edges. You see that it's narrow, and so it can detect any abrupt events like logging of the wood or forest fires and other things. And if you see the green, it's in between, so it's meant to detect like the drought, or which are somewhat gradual, the green with the scale 1. And if you see a blue one, it is like a broad one. It's meant to capture long-term degradations, like it can capture this kind of degradation over a decade-long signature. Like if you see, the NDVI is gradually decreasing, and this blue curve is meant to capture such long-term effects. Whereas this short-term effects, the red curve will affect, and we will have different scales, and we are going to correlate this kind of different wavelets with different scales into our time domain signal to get our wavelet transform, and see if we can see these 3 distinct ecological events in our wavelet transform. So here we have our time domain signal, the NDVI time series, and here we have different Mexican hats at different scales as we discussed. And here the bottom plot is our continuous wavelet transform results. And here what we observe is that Here the bright red spot at the bottom tells me that there is a land degradation happening, and this is what we show here, like the bright red spot, and in the y-axis it's the time scale of the events. So this bright red spot is happening at a 3-year time scale. So we have chosen only 3 time scales. So this 3-year time scale, it's a long-term cycle. So here we see one bright spot here, and this is happening at between year 3 and 4, and at the time scale of 3 to 6 months. If you see which time scale it is happening, it is at 3 to 6 months. So this is our drought here. So if you see there's a small drop here in the NDVI index, and that is reflected here in this patch. And similarly, if you see the insect outbreak at 7 and 8, between 7 and 8 year, that is what you see here in this patch. And if you draw a horizontal line, it corresponds to around 1 year period, or 6 months to 1 year period is what this corresponds to, this bright patch. And what is this? This is an artifact. Sometimes it happens because we are using these are the boundary effects in the wavelet transform. So what I mean by boundary effect is that at boundaries these points don't exist, and actually this creates artificial correlations at longer scales near the edges, and that's what we are seeing, this bright spot that we can actually ignore it. So to handle this, there are other techniques to actually use cone of influence, or we can pad data, or we can artificially extend the data to remove such edge effects. And anyway, we should focus our analysis only on the central regions away from our boundary, because our signal starts from 0 to 10. We should usually ignore the what is happening between 0 and 1 and 9 and 10. And we should only see the signals between like in the time scale of this region. So the reliable analysis region for a time series that is going from 0 to 10 years is that we should only consider it between 2 and 7, or maybe 1 and 8. So between 1 and 8 we have to consider what is reliable result. Other than that, we have the boundary or edge effects. I hope we have understood briefly about wavelet transform, how it works, and what it can do, like at different time scale and different frequencies, how it captures. Although this is a very vast topic, like the boundary effects, how we can deal with that, or what are the different types of wavelets, it needs like we can do many more videos in this topic. But for now, I think this video has come to an end. Thank you for watching so long. I hope you enjoyed the video. Remember to keep learning and enjoy life. Thank you.